So in the last sessions, I introduced the work. So in these sessions, I'd like to show you the work is related to kinetic energies. The kinetic energy of a particle is defined K equal 1 over 2 mv squares. M is the mass of a particle, v is the velocity of a particles. And the kinetic energy is closely related to work done on the object. We call such a relation the work-energy theorem. Total work done on a body relates to the body's displacement, as well as the change in the speed of a body. This displacement vector is parallel to the force. Force is parallel to the displacement vectors. Then work becomes positive. So in this situation, in our daily life, velocity of the object is increasing. We easily imagine the speed up. When the applied force is anti-parallel with respect to the displacement vectors, then speed is slowing down. So from a daily life, we easily imagine. So in this situation, the work is a negative. In the negative case, negative work, the speed is slowing down. In the positive work, speed is increasing. When the work is zero, it keeps the same speed. So in these situations, a gravitational force mg is balanced with a normal force. When the applied force is F, is on a perpendicular with the ground, then to balance with the applied force, normal force is increasing to balance with the applied force. Then total force becomes zero. So even if the force is acting, extra force is acting on the object, normal force increases to make the net force to be zero. Then we can apply the Newton's first law. Result is a constant velocities, same speed. Then we'd like to find out the change in speed. So when the acceleration, the object has acceleration of a, velocity change is given by the v sub 2 equal v sub 1 plus at. And the position is given by x sub 2 equal x sub 1 plus v sub 1 t plus 1 over 2 at squares. So we can write under v sub 2 equal v sub 1 plus at. So from these equations, you can find the t equal v sub 2 minus v sub 1 over a. And displacement vectors is expressed x sub 2 minus x sub 1. So we have expression of the x sub 2 substitute v sub 1 t plus 1 over 2 at squares. Then you can substitute this t here. Then v sub 1, v sub 2 minus v sub 1 over a plus 1 over 2 v sub 2 minus v sub 1 square over a. So from these equations, you can calculate v sub 2 square minus v sub 1 square over 2a. Okay, s is expressed b sub 2 square minus b sub 1 squares over 2a. So we have this expression. Then work, total amount of work done on this object is W, is F times S. So F is a Newton's equation of motion, ma. Then mas. Then as, you can find as. So from these equations, as equal 1 over 2 b sub 2 square minus b sub 1 squares. Then you can substitute here. Then you will get this equation. So total amount of work done on the object is equal to the 1 over 2 m b sub 2 square minus b sub 1 squares. So this is we call the work energy theorems. So work is equal to the change of these quantities. So work is equal to this quantity. So if we choose a k is a kinetic energy 1 over 2 mv square is a k is a kinetic energy, then work is equal to the difference of the kinetic energy k sub 2 minus k sub 1. We call that this is a work energy theorems. Work done by the net force on the particles equal to the change in the particles' kinetic energy. This is the work energy theorem. The work energy theorems. When the work done by a varying force, the force is changing dependent on the positions. But in this case, we just only consider straight motions. Then accelerations is expressed dv dt. Then we apply the chain rule here, chain rule. So dx dx. And then dx dt, this is equal to the v. So we can move to the next line. Next, v times dv dx. So a is expressed if you change this dx into the right, a dx is equal to v dv. So we have an important equations. A times the dx is equal to the v times dv. The work can be calculated with the integrals of the f with respect to x. Then f equal ma using the equation motion. So next lines. For the a dx, you can substitute. A dx is equal to v dv. So next line, v dv. Then we could perform these integrals. 1 over 2 mv squares. Lower limit is v sub 1, upper limit is v sub 2. Substitute. It becomes 1 over 2 mv sub 2 squares minus 1 over 2 mv1 squares. Actually, this is k sub 2 minus k sub 1. Okay. So, work energy theorems. This is still, we can still use the work energy theorems when force is dependent on the positions. Then work energy theorem on a curved path. Our object is moving on a curved path. Then again, we take a small element on a curved path dr. Then work can be calculated dw. dw is scalar product f dot dr. Then on this small element, we consider this is straight path. This is exactly equal to dk. So you can take a small straight path. This is some of a number of the straight paths you could consider. Then finally, work is equal to the change of the kinetic energy, even the object is moving on a curved path. Final topic in this session is power. Power is how quickly work is done, time rate at which work is done. Average powers is a delta W over delta T. This is the definition of the average powers. So once we define the average powers, we could define the instantaneous powers using the derivatives. Taking the limit of the delta T is approaching the 0. So power is equal to the dW dt. And the dW is F times ds. ds is a displacement vectors. So F ds dt, you can change. ds over dt is equal to v, is a velocities. So power is expressed F times velocities. Force times the velocity becomes the power. So unit of the power is expressed work this is a joule is a unit of the work. Unit of the time is a second. So joule per second. This is we call the watt. Watt is a unit of the powers. Okay, this is the end of this session.